Welcome to Paradox number 131, and today we are talking about cars in crosswinds. So cars. For many years, the drag coefficient of a car was given as almost the sole focus of any aerodynamic research on cars. But the lift of a car is also important, and one major reason why the lift is so important of a car is because it can greatly affect the car stability. The lift is proportional to the velocity squared. So like drag equals half times the density times the velocity squared times the area times the drag coefficient. Lift is the same thing, it's proportional to the velocity squared. So at higher velocities, the lift becomes non-negligible. For example, at low speeds, lift doesn't really matter too much. I mean, at 10 km per hour, or like 7 miles per hour, you might generate a couple kilos of lift, so just eat a couple of cheeseburgers and you'll balance that out. But at high velocities, like 100 kilometers per hour, the lift produced can be 500 newtons or even 50 kilos or even more, so 100 kilos or more. This is not nothing, this is something, and will reduce the friction on the tires and the road. Also, depending on where the lift is generated, the front wheels may experience more or less lift than the rear wheels, which changes the handling characteristics of the car. This can lead to a loss of stability, and reducing stability can cause car crashes. So if you were to look at when they put different flow control devices on cars, for example, the rear wing, that changes how much downforce is on the rear wheels compared to the front wheels. And that proportion there greatly affects how much the car can really handle around corners. So drag is not only important, but lift is also important when designing a car. Now, the other thing is that cars don't just travel in straight lines, they also corner. Even muscle cars, which do their best to only go straight, have to corner at some point too. So what's more, almost always, cars will be operating in a crosswind condition. If you think about when you're walking around outside, almost never will the road be perfectly aligned with the direction of the flow. So almost be never the case that you'll have a constant like head-on or tailwind. Now, obviously, winds are often not as fast as how fast you drive in cars, so you might drive at 100 kilometers per hour. The wind might be 5, 10, 20 kilometers per hour. But that's still a decent amount to change that angle to being non-zero. Now, the thing is, most aerodynamic testing of cars occurs with head-on winds. So more research is needed regarding how the lift and drag of cars are affected by crosswinds, and that's what we're looking at today. We touched on it a couple podcasts ago, or 3 podcasts ago or so, but I wanted to look into it even more because it's a really good topic to look into. So what's more, the underbody of the car has been found to significantly impact the aerodynamics of a car. So for example, we found maybe 10 podcasts ago or so that the underbody of a car contributes to like 40 to 70% of a car's downforce. So the rear wing, and like any other, the diffuser, for example, they're important, but the underbody going to the diffuser is just as important as well, if not more important. So that has important implications for aerodynamic testing of cars, because if you try to test a simplified car where the underbody is smooth, which we'll get into in a second, then you run the risk of having erroneous results. A lot of cars don't have smooth underbodies. They have quite jagged ones with, like the tailpipe showing or the drivetrain or whatever. So this is what we're looking at today, how the underbody is affecting the aerodynamics of a car in crosswinds, and how do different crosswinds affect the car's aerodynamics. Not only the drag, but also the lift, and also the side force. So to do that, we're looking at a paper called Numerical Investigation for the Influence of the Car Underbody on Aerodynamic Force and Flow Structure Evolution in Crosswinds. This is open access, so you can find it in the link in the description, and so you can follow along at home if you like to. And if you're listening to this on Spotify and or Google or whatever, you can watch the video on Spotify and YouTube. And on YouTube, we have other goodies for you that you probably enjoy too. So this study is primarily using RAND's CFD. It has some experimental data to help validate CFD, which, by the way, I hope they used an instrument to measure the density of air during their experiments, because the density of air changes by 2 to 4% on a regular day. If you want to see how much it changes with temperature, barometric pressure, and humidity, head over to our website where we have graphs showing this. We also make an instrument called the Atmosphere Hawk that actually measures the density of air for you and removes this error. Because in a case like this, if they were to use the experimental data to validate their CFD but didn't take into account the density of air, not only is there a significant error in the experimental measurements, but in their CFD as well, because the density they have specified in their CFD is almost certainly not going to be what was in experiments, especially considering that the density of air changes throughout an experiment. So for example, in your CFD, you might specify 1.2 kilograms per meter cubed, and in your experiments, you might have it ranging from 1.16 to 1.21 perhaps, and it just fluctuates throughout your experiments. That's a problem. But let's move on to their setup at least. So the velocity of the flow that they simulated with their car was 120 kilometers per hour. And this is about what most manufacturers test their cars at. Most have certain velocity ranges, with 140 km per hour being a very common one as well. But 120 is quite good. So why do they test at such a velocity? One major reason is for the standards put out throughout the world. So for example, something called the WLTP. This is a standard that all cars can follow to measure how much pollution they're putting out at a certain velocity range, and you can look at different velocities there. The other reason why it's so high is because when you go past about 60 to 70 kilometers per hour, I should get up paint here actually. So I've got my little paint tablet here. If you have a graph showing the x-axis is the amount of drag that or amount of resistance that the car is producing, and you have the velocity. You have the velocity here, and the drag will start to increase non-linear. Obviously, it goes to the velocity squared, and at about 70 kilometers per hour, 60 to 70 kilometers per hour, you start to have the rolling resistance crossing over the drag. What this means is the amount of resistance that the car is experiencing is the majority of it is coming from the drag and not the rolling resistance. Below 70 kilometers per hour, most of the resistance is coming from the rolling resistance and not the drag. So above 70 kilometers per hour, that's when the aerodynamics of the car starts to take over in terms of its performance and not the friction of the wheels to the road or anything else. So 120 kilometers per hour is a good velocity to test that. Let's look at some of the geometries that these researchers investigated. Figure 1 shows them both. They are both sedans. Both geometries have the same upper bodies and wheels. A couple of things to note are that the wheels have completely covered rims, and they slice through the bottom of the tires to produce the familiar contact patch. Apart from that, there are a few simplifications that have been made to make this simpler to do the CFD on, and they do change aerodynamics a little bit. Let's get into some of these. One of them is the tire bulge. So if we look at the wheel here and the tire where they've cut through, you can see on these figures that they have cut them through as well. This is not how a typical contact patch actually occurs. So in real life, what happens is that you have the wheel, the rim, which is obviously a metal. It's an alloy. It's very strong. It doesn't really deform very much. But then you have the tire, and that's made of rubber. That deforms. If you put more loading onto it, it's squashing more into the ground, and that deforms the tire. How does that do that? So you have the loading coming down, and where you have the contact patch, that's where the tire is hitting the ground, obviously. Then around that, because you're squishing the tire into the ground, it sort of bulges out to the sides. That makes the tire width at the bottom greater than the rest of the tire around the rim. So that's called a tire bulge. That does affect the aerodynamics coming around the wheel, and the changes that you'll be expecting are around maybe 5%, 3% in the drag coefficient. So simplifying that means you're going to have that kind of error coming into your experiments or your CFD. Another simplification that they made is that there's no cooling flow. And if you've actually watched one of our recent videos on automotive aerodynamics, we went through the cooling flow and the cooling drag associated with cars and what that is. You can find that on YouTube on our automotive aerodynamics series. I think it was automotive aerodynamics number 10, around that. So here we have no flow going into the radiator and coming out elsewhere. And this is a problem because with cooling flows, if you watched that video as well, you'll know that cooling flows typically increase the drag by about 30 counts, the drag coefficient, so 0.03. Now with electric cars, it's not as much, but I'm not sure whether this is an electric car or not. I'm assuming this is just a regular ICE car. And with that, you're going to be getting about a 30 count increase with the radiator flow taking into account. So apart from that, the car is featured in two different models, the Model A and Model B. The main difference between these two models is that Model A has a flat underbody, while Model B has an underbody similar to that of cars. So you can see all like the exhaust and the spare tire and all the other junk underneath there is fairly exposed. One thing to note here is that cars more and more are featuring these underbody covers, as you see in Model A. That is where you have these big plastic sheets and you cover the underbody stuff. The main reason for this is to reduce the drag of the car. And this is done in a couple of main ways. The first way is that you obviously don't have all these bits and pieces protruding into the oncoming flow. And the second major way is that the diffuser works better because the air hitting the diffuser going into the diffuser is more uniform and clean. Whereas if you have like Model B where you have all this junk underneath which is exposed to the air hits this stuff and it might separate, it might not, it might increase in velocity, might reduce in velocity, who the hell knows. So by having the flat underbody, you can skip over all of this stuff and you can keep the flow attached and more uniformly like flowing. That means you can design your diffuser to operate under better conditions. So just a note on how much drag the underbody coverings save the car. Generally speaking, like you're looking at about 5 to 20 counts. That's a general ballpark. So while Model B represents many cars, Model A with the flat underbody is starting to represent more and more cars these days. Hence, both models are applicable today. So let's briefly discuss the setup of their CFD. So they've done RANs here. And one thing that I want to talk about is the domain that they have their car in. So they have a fairly small box for this domain. The car is positioned here, you can see in figure 2. Only 3 car lengths from the inlet, and that's a little bit close. Going back 5 or even 7 car lengths downstream is a better idea. However, this comes at the expense of more cells, which they may not have the resources for. So the reason why you want to put the car further downstream is because of upstream effects. You have the car here, and it may be producing wakes and vortices. Well, that has upstream effects, and that can affect the inlet. So the inlet conditions that you usually specify is just like a uniform flow coming through. If you have all these flow features kind of messing with that, in real life you wouldn't have this uniform flow. Because at this point, you would have a uniform flow much further upstream. And that changes, like kind of forcing the flow to hit the car in a uniform way when it wouldn't be doing that as much in real life, if that makes sense. Overall, you just want to put this inlet further upstream from the car. 5 lengths, 7 lengths is good. Also, the walls to the side are a little close. There are only 3 car widths from the edges of the car, which is again quite tight. You don't have much room for the flow to develop and to potentially separate. So one thing that having the walls very close to the car will do is you're swishing the flow very close to the car. And that means that you're kind of forcing the flow to stay attached more because the flow doesn't have room to detach. And that changes how the flow physics occurs, obviously the drag of the car. The outlet in this case is not too bad. It is 7 car lengths downstream, which is starting to become okay. A more general rule is to be about 10 car lengths downstream or more. But in my experience, this usually only changes the aerodynamics by a couple of %. So 7 car lengths downstream is not too bad here. The Y plus values, which indicates how well the boundary layer is resolved in the CFD ranges, ranges from 30 to 200, which is fine in this particular case because they're using RANs with a K epsilon terminus model. It's actually the realizable K epsilon terminus model. So the realizable K epsilon terminus model is not my favorite. It was okay in automotive aerodynamics maybe 10 years ago. That was the standard. These days, a more sophisticated terminus model is usually used. In particular, the K omega SST one is starting to gain quite a bit of traction. I've seen quite a few papers lately over the last 3 or 4 years perhaps using this model because people are realizing that it is significantly better. And also when the cars are becoming more streamlined, that is also a better model to go for as well. So K epsilon is okay, but it's a little bit outdated in this case. One thing that I want to talk about is the wheels were not rotating or even had a rotating boundary wall condition on them. If you've listened to any of other podcasts on this kind of thing, you'll know that there are a few different ways that you can not just have the wheels rotating, but mimic them rotating in CFD. The obvious way to make them rotate is actually to make them rotate. You use a sliding mesh and you rotate the mesh around with your CFD. But that's quite expensive. A much more common way is to use something called an MRF or even a rotating wall condition. Both of these ways, they're like pseudo rotation methods. So what you do is you just specify, okay, the wall, in the rotating wall one at least, the wall is moving at this velocity, but it's not actually moving with different time steps. You just keep the tires and the wheels at the same geometric position and you just say, okay, the velocity is going to be this on the wheels. And you factor that into your equations. In this particular case, they're not even using that. So is that a problem here? Well, first of all, the car in experiments didn't have a moving ground system. That means that in experiments, the car's wheels were stationary too. So that means that the CFD matches the experiments. That's good from this point of view. you want your CFD to match your experimental setup as closely as possible. You don't want to be having differences, otherwise you're comparing apples and oranges, not apples and apples. From a real world point of view, having these particular wheels not rotating is somewhat acceptable here because the rims are completely covered, so there are no spokes chopping through the air. That's one benefit here. As such, it's really only the friction of the tire that results in the rotation of the wheel affecting the flow. If you have a slick tire, especially with no grooves, then the flow physics of the tire is not changed that much compared to when the tire is rotating. One of the major differences is that the inner vortex of the horseshoe vortex that forms around the contact area patch is diminished a little bit. So let me explain this horseshoe vortex here. If we have, let me go to paint here actually, this would be easier to show here. If we have the, let me plug in my little tablet. We have the wheel. Let's say we're looking at it from the back and like this. So we have the contact patch down here. Around one side, let's say this is the outer side and this is the inner side. We have one vortex coming around this side, the other vortex coming around this side. And this forms a horseshoe vortex around the front of the tire. So with the rotation, the inner vortex actually gets affected quite a lot. So in this particular case, we do have that inaccuracy in our CFD, but that's again only a few percent difference. So overall, this CFD might be 10 to 15% inaccurate overall, but the trends will probably still stay the same. So that we can trust the CFD to that amount. So another effect of the rotating wheels is that tires start to expand in the radial direction because of the centrifugal forces. So the tires, as I mentioned, are made of this elastic material, this rubber. So if you start spinning this rubber, the wheel will actually start to fling out in a centrifugal manner. And that means that the wheel will become thinner and it will expand out in the radial direction. The diameter of the tire will get bigger. But this is not actually much of a problem here, because in this context at least, because these tires used in this setup could just be approximated to smaller tires that become these dimensions upon spinning. And that is because there are so many different tire sizes that you can easily find tires that would approximate these dimensions when spinning. So that's not a big deal here. So that's the CFD setup and some of the benefits and some of the weaknesses of this setup. Overall, I would probably say that this setup is good to within maybe 10% accuracy, which means that we can use this data for the trends, not necessarily the numbers, but the trends will be okay. We can trust the trends. Let's move on to the validation of this CFD setup. So in figure 4, we have the flow over the backlight and the rear part of the car from CFD on the left compared to the PIV results in the right. And surprisingly, the results are very nice. Like the size and the shape of the wakes are very close, as are the points where the flow stops being fed into the main vortex behind the car and goes down to the ground. So you can see here this main vortex region, which is very common in cars. And then you can see this point just below where the arrows dive down to the diffuser area. This also occurs with the PIV. One slight difference is perhaps the vortex in the CFD is a little bit bigger and extends further down the back of the car than in the PIV. That's to be expected, though these differences may occur. So the qualitative comparison shows that the CFD performed pretty well. Figure 5 shows a comparison of the CFD and experimental lift, drag, and side force coefficients, the quantitative side. And they're all in very good agreement. The side force coefficients start to deviate at a little at yaw angles above 9 degrees. So if we look at figure 5 here, we can see that this is CFD are usually the open symbols and experiments are the closed symbol. Oh, sorry, the other way around. The open symbols are the experiments and the closed symbols are the CFD. We can see that at 9 degrees, this line here is the yaw. Below that, the CFD is mimicking the experimental yaw coefficient quite well, of the side force and coefficient quite well. Above that, it starts to break down a little bit, and that's probably due to a separation over the bonnet and the roof. The lift coefficient is consistently about 20 counts too high. So this bottom line here, this is the lift coefficient, and you can see that the CFD is always a little bit high, a little bit lower, than the experiments by 20 counts. indicating a systematic error. However, the trend found in experiments is matched very closely by the CFD, and that's pretty good. That's what I was mentioning earlier, where the trends seem pretty good, but the exact numbers are sometimes a little bit off. Moving on to the drag coefficient, we can see that it's quite good. The CFD matches almost perfectly with the experiments. One thing to note here is that the errors of the wind tunnel are not given. At least I couldn't find them. That is important because if the errors in the wind tunnel are 3 or 4%, then all of the coefficients found in the CFD start to look even better and even more agreeable, because now we have these error bars sort of encroaching each other, and the experimental data might be closer to the CFD than what we're seeing here. Now, we don't know what the experiments the errors in the experiments are, so we can't make that call. But overall, the trends look very nice, and even the quantitative data looks pretty good. From all of this, we can conclude that the CFD looks to be well validated for the drag coefficient particularly, and fairly well validated for the lift and side force coefficients. For these latter two coefficients, the trends definitely look good though. I should also note that it is quite difficult to validate a car with different yaw angles, and the simplifications here definitely made the process easier for them. So with having the closed, like the covered underbody, for example, that helped them validate their CFD. So that's the end of this podcast. We're going to be going into the results of this setup in the next podcast. We've gone through in this podcast the idea of the yaw and the effects of the yaw on the aerodynamics, as well as setting up CFD for simulating a car with stationary wheels at least, and the simplifications they made and how those simplifications affected the accuracy of the results. And we did the validation of the CFD. In the next podcast, we'll be going through the results of this CFD now. So if you like this podcast, make sure to like it. And if you want to see more like this, make sure to subscribe. And if you want to see other podcasts, check out our podcast playlist and also on our Spotify playlist as well. And if you want to get better at CFD and or theory like we've been going through here, check out our course link in the description. And if you want to get that Mr. Hawk, which I mentioned earlier, that's an instrument that makes your experiments 2 to 4% more accurate, because the density of air does change by that much every day. And if you don't take into account that change, then your experimental data has that error in it. And what's more, if you try to validate your CFD with it, then you're going to get that error as well. In this particular case, I doubt that they did measure the density of air because they didn't mention it from what I could tell. So that's also another error in here that could alleviate some of these differences, or they could exacerbate them. We're not really sure because we haven't got the data. So that's one problem that CFD runs into with experimental validation, when we don't have that density of air tightly nailed down. The Mr. Hawk gets rid of that error for you. You can find it in the link in the description. And I'll see you next podcast. Peace out, amigos.